We present MeshVPR, a hybrid VPR pipeline that leverages the increasing availability of 3D meshes of cities. We demonstrate how we can deploy a VPR system within a day to locate images in any target city where a 3D mesh is available. For example, let's search for the location of the Brandenburg Gate. In the following minutes, we will explain how to set up this pipeline using a simple recipe. But first, let us briefly introduce Visual Place Recognition, or VPR. VPR is the task of recognizing the location of a given image and is usually addressed as an image retrieval problem. An embedding of the query image is matched against a database of images for which the location is known. To get accurate results, a broad and dense database of geolocated images is required. Collecting a database is therefore a costly and time-consuming task and is often overlooked in previous works on VPR. An alternative to collecting real images is using synthetic images generated from photorealistic 3D meshes. Unfortunately, as can be seen in the figure, VPR approaches trained on real images struggle with the domain gap between synthetic and real images. To solve this issue, we present MeshVPR. MeshVPR consists of two phases, the training phase and the deployment phase. The first step of the training requires us to obtain a dataset where both real data and a 3D mesh is available. This can be a real dataset and 3D mesh for any city. Even though we want to deploy on Berlin later, we use a real dataset and mesh of San Francisco for the training. The next step involves generating matching synthetic images for the images in the real dataset. Let us look at some examples of the collected pairs. Those pairs once again outline the domain gap between real and synthetic data. This domain gap is addressed by the core step of MeshVPR, the features alignment step. We begin by downloading a pre-trained VPR model, which we depict in blue. This model will only be used to extract features from real samples, so it will not be further trained. We utilize a second model and we initialize it with the weights of the reference model and train it to learn the alignment of features from synthetic samples to real samples. In the deployment phase, we create a synthetic dataset for any 3D city mesh or set of cities. The database of geolocated images is created by sampling the 3D scene within specified areas. First, we generate a continuous path through the sampling area using street network data from OpenStreetMap. We continue by rendering images along the generated path similar to how a Street View car would capture images, with the difference that we are not constrained to streets and can even sample data from blocked areas such as this construction site. In addition to using data from OpenStreetMap, we use the collision data of the mesh. We use the data to refine our sampling locations, to align them with the mesh and steer them clear from obstructions that would block the view, such as trees and cars. To wrap this up, let's look at one more example query.